Hello, my name is Thiel and I'm a professor at the University of Aberdeen in Scotland. I use mathematics and data to make sense of the world and try to understand how it works. It's a great pleasure to speak at the King's Academy COVID-19 Symposium. And I think it's really important because we all face a pandemic and large parts of the world are in lockdown. People are at homes. People are sick in hospitals, people are dying, people fear for their loved ones. The economy is in free fall and lots of health systems all around the world are in lockdown. So how can we use mathematics and mathematical modeling to take decisions about how to proceed? What should we do in the future? How should we ease restrictions on people? What is the best way forward? Very often, politicians, decision makers are informed by scientists based on mathematical models. These models allow us to study how diseases can spread and how societies could react and see the consequences of our actions. However, these models also have drawbacks. Not everything always works. Sometimes decisions being taken based on these models might be wrong because the models are wrong. So how can we understand how models can be used and what we can do mathematically to help people get out of this situation? In the next 10 or 15 minutes, I will show you how to develop these models. You will develop these models with me, and you will be able to play with these models and try them out. And we will then look at a couple of consequences that these models have, so kind of ideas that come out of these models. And we'll also see a little bit where we have to be careful when we use these models. So let's start with that. Okay, so I have prepared some slides and we'll walk a little bit through the process of building a model in order for you to be able to do the same thing at school. I have prepared these slides in a way that you can basically go online and you can interact with these slides. You can change your own parameters, you can change the models and see what happens. So there is a QR code here on the right-hand side, and if you scan that, then you will find a website on which you can find the slides and you can interact with these slides. So the first thing we want to do is we want to get into building our own model. Well, how do we build a model? Now, mathematical models are a simplified description of the world. And in order to build our own COVID-19 model, we will also have to simplify the world. And I'll show you how this can work. So let's assume, and this is a simplification, that we can split our society into three groups. There is a group called S, I, and R. And the group S are the people who are what's called susceptible. They are people who can still catch the disease. They have no immunity, they have no vaccination or anything. They are susceptible to the disease and they can catch it. Then there is a group, I in this model, and those are the people who are infected, who have the disease at this point in time. And then there is a third group of all the people who have either recovered or have died. Now, these three groups are built in a way that we assume that everybody in the population has to be in one of these groups. They have to be either susceptible or infected or recovered. There's no other way for anyone to be in the society. So we would like to build a model to see how you can transition from being susceptible to the disease to getting infected to recovering. So we want to model this entire process. And what we want to do is we want to describe this in mathematical language, in mathematical equations. Now, when I see equations, for me, they tell a story. Let's tell our story in mathematics. So we want three groups. One group will be the susceptibles, one group will be the infected, and one group will be people who have recovered. And we want to see how these groups change over time. So how many people are in these groups as time changes. Okay, so we need something that tells us about time. And what we'll do is we write little brackets and say T, where T stands for time. So what this does, it basically tells us the number of susceptibles and infected and recovered at time T. So what I could do is I could say, well, if nothing happens, If nothing's going on, no infections, no recoveries, well, then these numbers won't change over time. So my susceptibles will be basically the same as we had in the last time step. Nobody will get out of this group or into this group. And we could say the same for the infected and for the recovered. So in this world, you can't actually get infected and you can't recover. Everybody stays as they are. You have to be in one of these groups, so they have to add up to 100%, so you have to be in either of these groups. And now we want to describe how you can actually go from one group to another one. Well, how do you get from a group, from the susceptibles to the infected? You have to catch an infection. How do you catch an infection? Well, when a susceptible meets an infected. Meeting in this case means I have to multiply these two numbers. So I get out of this group, that's a minus sign, and I take the susceptibles at that time and multiply that with the infected at that time step. Well, turns out that not everybody, every time a susceptible meets an infected, the susceptible becomes infected. There's only a certain rate. We call that the infection rate. Let's give it a name. Let's call it rho. So with a certain rate, now an infected person can infect a susceptible. And then they move out from the S group into the I group. So they move out here. Well, we have to put them into the infected group because that's where they're going. But they go into this, so they get a plus. There's one more thing we need. We want people to be able to recover. There is a certain rate with which these people recover or die. Now, that means I get out of this group and I go into the recovered group. So my infected people can get out of here and they can get into the recovered group. But not everybody who's infected will automatically go into the recovered group. Again, there is only a certain percentage, a certain rate attached to it. Let's call that rate lambda. And because they go out with a lambda here, we also will need a lambda here. And that's our model. This model now describes that, well, the people in the susceptible groups will be the ones who were in the susceptible groups in the last time step, minus the ones who got infected. What do these people do? Well, they move into the group of all the infected, but there are also some people moving out of that group because the ones that recover go from the infected group into the recovered group. We're not quite done yet because we can only say how many people will be there in the next time step if we know the previous time step. So we need a starting point. So we could do something like, say, we take the susceptibles at time 1, and we say in the population there are 95% of people who are susceptible. Everybody in the society, or everyone together, need to add up to 100% or to 1. So let's say we have at time 1, 0.05 infected people. That's 5%. And you'll see that the 95% here and the 5% there add up to 100%. So in our recovered group at that time point, there will be nobody. Two numbers are missing now. We don't know yet what the rho is and what the lambda is. So how many people get infected by an infected person and how many people recover and how fast do they recover? These would be numbers that we get from data, from measured data, from observations. But what we do here is we'll start and say, we'll take the rho to be 0.2 and we'll take the lambda to be 0.1. Now our model is complete. We have the equations that tell me how things change over time. We have conditions to start with, and we have these parameters. Let's run this. So here are our equations. If we run this, that is the result. The green ones here are the infected people, and you see there is a little peak here. The red ones are the ones who are susceptible, so they become less and less because susceptible people can only go to infected and then recover. And the recovered people, that number goes up over time. If you go to any vertical slice here, these numbers will add up to 1, and we can represent that if we just stack these numbers. So how many people are susceptibles, how many people infected? So at the beginning we have 95% susceptibles, 5% infected, and you see the orange band here, that's kind of the people who are infected, the blue, the ones who are susceptible, and the green ones are the ones who have recovered. And you see in this case, lots of people at the end will have recovered. Some people never got the disease, and still the disease kind of dies out. That's what people refer to when they speak about herd immunity. We can also make interactive diagrams. So you could now change the recovery rate and the infection rate. If I make the infection rate worse, higher, you see that this peak here will become higher. If I make the recovery rate lower, the peak gets even higher than that. And there will be a critical moment when the infection rate becomes lower than the recovery rate, then my peak will just go away and I will have no outbreak. So infection rate lower than recovery rate means no outbreak. And as soon as my infection rate gets higher, I will have a little outbreak here. And if it's really, really high, my outbreak will get worse and worse. Here's the same picture stacked. So you would see all the people who are susceptibles, the infected and the recovered. And again, we can change these numbers and explore what our model tells us about the real world. So how can we use these models? If we have a model like that, well, first of all, this model is really, really simple. We probably want to make that model more complicated. We have built these models. So for example, this model, where every point here is its own model, and they are connected via flight connections. These are all sorts of airports around the world, and there are flight connections between them. Now, if you hop on a flight, you can take the disease with you. Now, in this case, the disease starts here somewhere in West Africa, and it spreads all over Africa first, then infects Europe, starts infecting the United States and Asia, where the outbreak will come a little bit later. Then Europe recovers, and at the end, the entire world has recovered. So we can actually build much more complicated models, but the basic idea is the same. Now, how can we use that to make decisions? If these models are there, we can now put things into these models to see hypothetically what would happen if we did a certain thing. Here's data from another pandemic that happened in the 1980 about, and this is the Spanish flu, and this is data from the United States. So what you see here is the number of deaths, and here is time. And these boxes here show you social distancing. So people were either locked at home, they were not allowed to go outside, just like us now. So what you see, Philadelphia, actually, they started a little bit late. They even had a large parade after the outbreak, and they started the schools a little bit, closed them late. So there was a huge outbreak, they had social distancing, and then everything came down again. Sometimes you will have multiple peaks. So you will have an outbreak here, there's social distancing, but when you relax social distancing, the peak comes up again. And this is data, observed data. If you make the social distancing longer, the outbreak might be smaller, or you might even repeat these social distancing periods. There's data from all sorts of American cities, and you see they did different things, and sometimes they had second peaks, sometimes even worse than the first, and sometimes they had several periods of social distancing. How would we do this in our model? Well, the infection rate here would change over time. You see now it's also got this kind of time parameter. And we could say, what would happen if we have social distancing? Well, the infection rate goes down because people do not get in contact. So I have here 3 different kind of scenarios. Let's start with short measures. High infection rate, social distancing, and the infection rate goes down, and then it comes up again. Longer measures, social distancing, and even after that, we still have some form of social distancing. It doesn't get up to the original values, or very low measures. Now we can put this into our model, and what we'll see is if we have short measures, short social distancing, we have a peak and then a large second peak. Longer measures and a very broad but not very high second peak. And very long measures, no secondary peak at all. So these kind of models can inform us how to deal with social distancing and how to manage a disease like this. And that's basically all I wanted to tell you today. I have prepared a last slide with additional data, additional papers and resources. If you're interested in this, have a look at those. You can also ask me by email anytime. I'm more than happy to help.